Thank you for joining us today for another Telops webinar. My name is Joe Carrock. I am a field applications engineer in the US for Telops. We are a part of Exosense Group, and today I have a presentation for you. It's a product-themed presentation on our HDR M700 titled Next Generation High Dynamic Range Infrared Imaging. And just before we get started, I would like to run our standard poll, which gauges your interest and knowledge level of infrared imaging. And this helps us gauge future content towards the appropriate level for our attendees. I will tell you that today, this presentation has something for everyone. This high dynamic range camera is a new product. It is extremely exciting, but even for folks that have heard about it before, we are talking about a few concepts for the first time today, and we have some new field collected data. So I think there will be something for everyone. Give another few seconds for some votes to come in. All right, so pretty good mix there. A lot of folks who have had some experience with infrared cameras before. I think that's going to be helpful here today because we are talking about somewhat of an advanced system, but a pretty good mix. So thank you for participating in the poll. And with that, we will take it away. So again, today's presentation is on the new HDR M700, which is a high dynamic range system from Telops, which due to a new unique digital readout integrated circuit, or DROIC, and advanced on-chip saturation management functionality can achieve seeing a dynamic range of over 900 degrees C in temperature with a single image, single exposure, single optical path in a snapshot configuration. So we're pretty proud of that. However, Telops also offers a full line of infrared scientific cameras, including hyperspectral systems, multispectral systems, high performance, high speed, and high definition infrared cameras, as well as entry-level systems. So if you do not necessarily need high dynamic range, or if you're interested in any of these other cameras, we won't be mentioning them too much today, but please do reach out to us. We would love to talk to you about your needs and any application in the infrared. So to get started, talking about a high dynamic range camera, we have to define dynamic range for an infrared system. And generally, dynamic range is the ratio between the smallest and largest values a measured quantity can assume. And for an infrared camera, we define in-scene dynamic range as the temperature range, which can be measured in a single snapshot image by that system. Typically, for an infrared camera, this is dictated by pixel well filling. So each pixel in an infrared detector can be seen as a well, which can accept a number or an amount of charge, an amount of photons. And typically we try and keep the amount of well filling in these pixels between 10 and 90%. This is to avoid saturation of the pixel on the high end, where data quality is lower or lost at a certain point, as well as to avoid noise floors on the low end. So for standard cameras, the range that we can see in dynamic range with a standard pixel is about 150 degrees C for a mid-wave IR system, or about 320 degrees for a long-wave IR system, which is a pretty decent range. However, if you're trying to image, let's say, ambient temperature backgrounds as well as a high temperature target, this might not be enough. You might have to shift and give up either the low or high temperature information. For example, you might be able to see the ambient temperatures or lower temperatures, but you might have saturation here like we have on the left in the green pixels with the mid-wave camera over your high temperature target. Or if you shift up to a higher temperature calibration, you might lose that ambient or lower temperature information. It might be lost in the noise and effectively blacked out. So to address this and to provide a solution when you do need to measure wide temperature deltas, Telops has developed, and we now are pushing the first deliveries of the HDR M700 before the end of 2025. So this is a real product here, the HDR M700, which expands in-scene dynamic range to over 900 degrees C in a snapshot configuration. So let's look at that graphically here. So on the left, we have a typical mid-wave IR camera. This is, you can see there between the 10 and 90% well filling levels, we have that green bracketed region under the curve. This width is the dynamic range, and in this case, it's about 150 to a little over 300 degrees C there. That's about the maximum that you're going to get out of a mid-wave camera there at 50 microseconds exposure. A long-wave camera, you would get slightly better results, about 25 to 325 degrees C. But if we look over at the HDR curve on the other side, the typical in-scene dynamic range for the HDR, you can see that those 10 and 90% levels fell out quite a bit faster, which gives us a much wider green bracket there at the bottom, or the dynamic range, 100 degrees C to 1,000 degrees C with a 100 microsecond exposure is what we rate this camera at. And I will say that in practice and in the examples that I have in the data section later on, we've actually seen this range go over 1,000 degrees C in dynamic range in a single snapshot imaging configuration with this HDR. We are extremely impressed and proud with the results. Just about every time we pointed at something new, we see something that we've never seen before and that we wouldn't have believed was possible with the previous generation camera. So there's all sorts of examples through this presentation. If you like or have any interest in any of this data and would like to learn more, please do take one of our emails off of one of these slides and reach out. We won't be going into direct detail on all of them, but it is all extremely impressive, the data and the imagery that this camera can produce. So a quick specifications table before we get into some of the operational management considerations for this unique system, and then into some data. So key specs for the HDR is its strained layer superlattice SLS detector with 3 to 5 micron spectral range. It is a VGA detector, so 640 by 512 pixels with 20 micron pixel pitch, and it can image up to 500 hertz at that full frame at 640 by 512. You can window down to get a little bit more speed out of the system, but I will say that this is not geared to be functional in that way. Similar to our fast cameras, you would not be able to achieve the tens of thousands of hertz that you might get with a fast camera in windowed mode. It is a different operating concept. We have to run slightly longer exposures to be able to see the lower end of the temperature dynamic range. So if you did need ultra high frame rates, you would want to look towards a different system. However, other key specs here, so the NETD is still very low, under 20 millikelvin generally, and a maximum of under 25 millikelvin, which is very good. And the system can accept all of Telops threaded lenses there, the 25, the 50, the 100, or the 200 millimeter lenses in the midwave format are compatible with this system. So let's take a look at the operational concept. I mentioned briefly earlier the ROIC, or digital readout integrated circuit. That is truly the power behind this system. It is a 23-bit digital ROID and detector combo, which allows for fill and reset operation, which essentially means that these pixels can collect an amount of signal and then can reset or subtract an amount of charge from that pixel well up to 255 times per image, per exposure, which allows us to use the extra bits here, the 23-bit architecture, to assign a number of bits to count the number of times that that well has been reset. So if we assign 8 bits to the count of the number of times that the well has been reset, we can assign the remaining 15 to the residual value, or to track the amount of charge or signal that is in the pixels at any given time, as well as at the end of the exposure. And thereby we can recombine after the image has been collected to multiply the amount of charge times the number of charge that has been subtracted from these wells, and then add the residual value. So I guess we should mention that calibration. It is still the Telops global permanent calibration that you know and love. And if you don't know and love it, I would encourage you to educate yourself with some of our other materials, because it is truly a superior user-friendly calibration in the sense that it is blackbody free and permanent for the life of the system. The calibration is done up in our factory in Quebec with flux-based lookup tables and high-precision blackbody sources, and you never need to recalibrate. You don't need to lug out blackbodies. You're provided with a pixel-wise nuke, as well as radiometric temperature, in-band radiance, or in-band irradiance output, and this is valid for the lifetime of the system. And again, this calibration is applied to the full detector 23-bit depth for full quantitative fidelity there. However, if you don't need to use Telops calibration, or if you are an advanced user, perhaps in infrared signatures with your own precision blackbodies, you also have the option to create your own calibrations, just as you do with all Telops infrared fast cameras, through the Telops calibration builder tool here. So this is an add-on tool where you can use your own blackbodies to create custom calibrations that can be applied to the data in Reveal IR, just the same as you would the Telops global calibration. So truly you have the flexibility as well as the power of the Telops calibration to allow for optimized radiometric performance across any measurement type. Okay, so with the fundamentals out of the way, I think the best way to show off this camera is actually just through the data. It provides an exceptional amount of new information that was previously unattainable by infrared cameras. So first here, we have a combustion experiment. This is quantitative blast analysis. So there was an energetic compound here that was detonated, and we are imaging this with a 100mm lens at about 700 hertz with the HDR M700. And I encourage you to look at the max temperature and range plots there. So the max temperature just after the detonation were over 1,000 degrees C in max temperature, but the range is also over 1,000 degrees C. So essentially, we're imaging the down to just above ambient temperatures. And we have a line profile there. You can see it moving. The deltas and the profile definition there is incredible. A previous generation mid-wave or long-wave camera would not have a dream of seeing this level of temperature differentiation, especially at the beginning of the sequence. We'll watch it come around here one more time. But it is absolutely impressive, the results that this system has been able to capture. And these are just some of our first tests. So let's take a look at a breakdown here. We'll zoom in and we'll pause a little bit. So this is just after the detonation, and we can see if we look at the zoomed in pixels there, that we are just up to the limit. So those OCR tags, that's actually over calibration range. So we have exceeded our 90% well filling, even with the extra bit depth and the reset mechanisms of the HDR, where we're willing to put error bars on our calibration. The data, however, is still being collected. In the raw data, you would still have signal there because we have not yet reached a full saturation point. That would get a different error pixel tag. So essentially, we're imaging all the way up to over 1,100 degrees C there. However, if you look at the range plot, we have the full range available to us. The range is also over 1,000 degrees C. So we're seeing those full gradients straight from over 1,100 all the way down to under 100 degrees C, which is exceptional. It's first of its kind type data that we are collecting with this system, and this is just the beginning. So one more example here. This is now an aviation example. This was collected just a couple of months ago at the Pacific Air Show in Huntington Beach, California. These are the Canadian snowbirds. They are a trainer pilot group. And I will admit, we do have some amateur tracking going on here. Can't exactly bring a professional tracking system to the beach. So this was done by hand on a tripod, but bear with us if you will, because what we can see here in these planes and in this data is pretty impressive. So we're displaying the data now in in-band radiance instead of temperature, but what you can see is the evolution of that radiance profile through different orientations and angles of the plane as they move away from us, as they move up and down, as they do their aerobatics. It is truly impressive that we're able to see all of this, whether it's the peak intensity levels when they are pointed away from us and we're looking directly down the exhaust in the engine bay, or whether they're pointed away and they're doing their loops in the air. The Telops camera, the HDR M700, this new high dynamic range system, is able to image all of that without losing any data quality, without saturation or noise issues. And no other infrared camera has been able to do that. So we're really impressed with this. One other thing for you signature folks that might be looking at planes, we do also have the ability to do atmospheric correction. Within our Reveal IR software, you can correct for things like atmospheric temperature, humidity, CO2 concentration to get calibrated results, even in radiance or in temperature, directly out of Reveal IR. And we do have an example of that on the next slide. So this is now a helicopter still at the same air show in Huntington Beach at about 1 kilometer distance. And we have applied, as you can see in the bottom left, the relative conditions for the day of the collection there. And we have activated it on the full scene, and all on the back end. Telops data management engine handles all of that, and it provides you with the calibrated adjusted result there. And we can see that even at 1 kilometer away, looking sideways at the exhaust vent on this helicopter, the signal level there is over 300 degrees C. And we also, as well as the hot temperature exhaust vent, we can see that tail, that hot gas exhaust as it gets back towards ambient temperature by the tail of the helicopter there. So truly impressive stuff. And you have the flexibility and the data quality, the quantitative fidelity to pull all of the data and information that you need here. So one more example, this is actually an experiment. So this is a collection that we ran using some high temperature lab sources. We have 2 black bodies there as well as a heat source. And we are comparing the HDR M700 to EHDRI or superframing techniques, which the HDR has essentially made EHDRI and superframing obsolete, especially for dynamic scenes, things like where there's movement or dynamics in things like energetics or ballistics, because in EHDRI or superframing, you used to have to use multiple exposures. And so what would happen is you would collect a short exposure, a long exposure, you would cycle this, you would have multiple pairs of long and short exposure that you could then combine in post-processing to achieve a dynamic range that was wider than you would be able to achieve with any individual exposure time. However, you have to give up frame rate to do this, to vary the exposures. And you also run the risk of introducing reconstruction errors in the post-processing, especially temporal reconstruction error. And that's exactly what we see here, even with this simple experiment. The HDR M700 is able to view everything because it is using this well reset mechanism. It is one exposure, it is able to see the low temperature black body at 100 degrees C all the way up to the lab heat source at 1000 degrees. And it is able to image them directly without any need for varied exposure, without any need for post-processing, so that there is no introduced error, and we have good spatial resolution, good data quality across all of those heat sources as they move throughout the scene. However, when we look at the result from the HDRI, it is very apparent the limitations there and the reconstruction error that's introduced spatially. So you can see it especially on the high temperature heat source, which we've put for the M3K. It is a pretty cruddy image, to be honest. There's not much information you would be able to pull out there, and certainly your radiometric accuracy would suffer as well. The M350 performs slightly better, but we see this ghosting effect right here, especially where this is a sort of ghost as the high temperature object has moved through the scene due to the reconstruction. There's also saturation. Neither of these would be acceptable to us in terms of data quality. However, the HDR, perfect image. I can't stress this enough. The types of imagery and the data quality that we're seeing with this camera, even from our first experiments and our first data collections, is superior to anything that we've seen before in terms of image quality with dynamic range. So we're very proud of that. And I know this was just a few examples today, but I will now move to close, and I will encourage you first, before I do, to take down our emails here. So the FAE@telops.com email, that one will get to the field applications engineers, including myself. If you would like things like data samples or to talk about advanced topics, if you would like quotes, timelines, or product info, you can also email our sales team there with sales@telops.com. And in either case, it will go to the entire team such that we can connect you with the appropriate member for your region. So again, the HDR M700 is a next generation 23-bit architecture, high dynamic range focused infrared system. And through its unique on-chip saturation management functionality and Telops data management engine, we are able to deliver precise, radiometrically calibrated scientific results with extreme snapshot dynamic range. And we think that this system will be extremely beneficial as a new tool to folks doing infrared signature measurements, ranging measurements, ballistics, additive manufacturing, wildfire and combustion, and a host of others. Essentially, anything where you need to view high dynamic range and you would previously have been stuck with techniques like multi-exposure techniques or superframing. So thank you for joining us today. That is our presentation. I will take a quick look here at the questions box. Okay, so we do have one question. How long does it take to reset the capacitor? Does that affect the minimum responsivity in terms of duty cycle? So the reset time, I'm not sure on the specifics of the way that the electronics work in terms of the duty cycle. However, the reset time is largely limited by the exposure that we actually have to run to achieve the low end temperature performance. So we have to run a longer exposure to be able to see those lower temperatures with good signal to noise. And this is actually what dictates our frame rate. So the speed of the reset is actually quite fast. And instead, we're limited by how long we need to expose. I'm not sure if that entirely answers your question. We might have to ask our engineers if you'd like to get more into the back end of the electronics and the. Excuse me, I hope you can hear me. My headset just turned off there for a second. It looks like we have one more question, and we're asking, how does this camera account for emissivity? So the camera itself would not account for emissivity. The camera itself would image radiometric temperature or in-band radiance or irradiance, which means that it is assuming it is looking at a black body or a completely emissive object as it was during our calibration in the factory. However, you can insert your own emissivity value in an emissivity correction tool similar to the atmospheric correction tool in Telops Reveal IR software. And so you can make an emissivity correction if you have a known emissivity value of your target. Okay, I think that's all we're getting for questions. I don't see anything else coming in here today. So one more time, I'd like to thank you for joining us. Thank you for being a part of this webinar, and we hope to see you at the next Telops webinar.